Hello, my AP Calculus BC friends, and we're back at it again for e-learning day 5. I want to start by thanking you guys, not just the 18 that are live, but those of you that are going to be watching recorded, or as we call asynchronous in the biz. Everybody got their quiz score in. You did fairly well with it, and it was a challenging quiz. I really felt that it was going to have some components of it that bothered you a little bit. But you guys did a good job with that. So you're doing everything that I asked you to do. I wish I had answers because I'm getting a lot of people that are asking things about, what's going on now? Restaurants have closed today. It's probably likely things are going to get maybe a little bit worse before they get better. But, all that we can do is just do what we do. We don't want to take anything that you've worked hard for, not just this year, but all of your lives in mathematics particularly, and let it go to waste, because I'm holding out a lot of hope that you guys are going to be taking the AP Calc exam and that we're going to do well, right? We're in a position to do very well. We're heads and tails above most of the population. I want to hopefully keep it that way. So, all right, we'll talk. Yeah, we'll talk about AP exams. I mean, no word is out, but the one thing that's nice is that I do have a little bit of insight. I have some very good friends that are very much high in the leadership, and they can certainly give me some information about it once the time comes. So, anywho, let's get a rolling here. One of the things that I wanted to do through this Zoom session is I wanted to talk about the quiz that you guys took online. But instead of just taking your Zoom time to do that, because I know some of you guys did so well on it, and others of you may have only missed one problem, two at the most in some cases, I am going to, believe it or not, post that key later on this afternoon, and I'll just leave it up all week, and you guys can open it up at any point to kind of see where things may have gone wrong if you didn't score a 10, or where things may have gotten lucky for you if you did score a 10. And it's all typewritten, and I think it should be pretty easy to follow. I thought about going through it problem by problem with this Zoom, but I'm really trying to keep these things short so that you guys can get on to your next order of business. All right, so that is the first thing I wanted to talk about. And the second thing I wanted to talk about, CMLs. I got a lot more information about the CML. I'm going to drag this in here, guys. And I'm going to show you what happened with Meet 2. And here we go. Here are our top 5 teams that scored a 60. So only 5 scored a 60, which is very, very cool. What that means is we lost about 3 or 4 teams that were tied with us. And I think one of these teams is a team that did not score a 60 on the first test. Because as of right now, if you can kind of read this, these are the 4 teams that are in first place. And you can see that, yay, Avon High School is one of them, with all of our good friends, High Tech, Palo Alto, and Naperville North. So we're doing great, you guys. We just got 2 more, 2 more to get in. There's where we kind of fit across the state of Indiana with the other 4 schools, Bar Reeve and Roncalli and Canterbury. And then let's also pay a little tribute to our big 3 here. One of them is with us, I think, here, Ahmed. So we have 3 people that are still in the running for a national champion status. This list is getting a little shorter every time, so apparently that last test was a little bit of a bother to some students. Now, as far as Meet 3 is concerned, we just received word from the Continental Math League is that we can take it late. We don't have to rush to get it finished before March 3rd or before April 3rd. So I won't be doing this whole spring break thing about bringing kids in optionally that want to take it. Guys, I really want you to relax on your spring break, and you're owed those 2 weeks. I feel bad enough that we talk about you working on a mock exam, but I really don't want you to have to worry about anything other than just recovering, relaxing, and then just waiting for what comes next, whether it's more e-learning or face-to-face. All right, so with that being said, I know some of you are thinking, oh, what about that little deal you made about having us do the 4 practice exams and then just get a completion grade and 2 automatic 10s. Well, that's going to be altered a little bit. but it's going to be altered, I think, in a good way. So if I like bring in Schoology here for just a second, I want to show you that whether you're in period 2 or period 4, your Schoology landing pages look the same. You now have a Continental Math League folder, and in that folder, there should be a subfolder called Meet 3, and in that Meet 3 subfolder, I do have 2 exams, and that's all that I would assign. Right? You don't have to do 4 exams and take your best 2. Just we'll focus on working on these 2 exams only, and we will work with those. In other words, those would be the 2 that are scored. You can start working on these as soon as you want. You can download them and print them. If you don't want to print them, you can just look off of the screen and do your work on a separate sheet of paper. These will not be due until the week we get back from spring break. All right. In fact, I'm going to set a deadline of Friday, and I believe that's like April's, not like the 10th or something. I'll get more details to you later, but it's something that you don't have to rush to do this week, but you can always get a start on them. All right. So, all right. Let's go ahead and move all of this stuff out of the way and focus on today's lesson, right? Today's lesson is a review, Euler's method, and it's very likely that a lot of you may have completely forgotten Euler's method. That's usually the case. It won't take very long to recap it, and this will also allow those of you working on your mock exams to not look at those Euler's method now problems and be like, what is what am I doing with those? Now you'll be able to remember how to solve them. And then fortunately, this will help kind of segue into tomorrow's lesson, which is a brand new thing that you haven't learned called logistic growth. Okay, so we're going to talk about these first, and then we'll discuss the short homework assignment that you guys have for topic 7.5 that you'll be working through the week. Okay, so if you got a chance to download the notes, they would look a little something like this. I guess if you don't have them printed out, you can still follow along. It's certainly a lot more effective if you can write on these. But you can always like rewatch the video, I guess, if you had trouble. So if you remember, Euler's method was basically a procedure that allowed you to approximate a value on a curve. Let's say that this curve looks like this. I want to change this curve a little bit, you guys. I want to pretend that it does this instead. There's no need for you to make any modifications. In fact, I'm gonna use my white pen and get rid of that. How's that? So let's say that this orange graph is the actual solution curve to the particular equation that I would like to solve, that particular differential equation. But let's say for some reason, whatever the case is, I can't solve that differential equation, and I can't take the integral and figure out what that curve looks like. Well, I can start doing a lot of other crazy things, like take tangent lines to that curve, starting at a point that they might provide, and then let's say the ultimate goal is to figure out what is the value of the curve right here at, say, x sub n. So in other words, my ultimate goal is to figure out what is this? Man, I would love to know f of x sub n. But all I have to work with right now is that first tangent line that if I extended would look something like this, possibly give me this y value over here, right? Which isn't the best y value because it's a little far from the one that I want that's highlighted up here in this beautiful green color, let's say. So then we redirect the tangent line, so to speak. So we have a certain distance that we're given that we can work off of. We redirect that tangent line. Now we have a tangent line that's going to be looking something like this. It's still going to like adhere to the curve, but it's just not going to be attached to the curve anymore, right? And then I might use this point, the point that I'm now coloring in this lovely purple. And maybe that point would be a better approximation. And no doubt the difference between those two is certainly smaller. And we could say that that's a halfway decent approximation. So that's what Euler's method is all about, in case you had forgotten. So we're going to go ahead and start it from scratch here with our first example and get you kind of reacclimated to this. It says use Euler's method to approximate the particular solution of the differential equation y prime equal x times y that passes through the point 0, 1, and it uses a step size of 0.2 for the h. And I have this set up where we're going to organize it in a table. So the very first thing that we're going to do is we're going to drop down our x value that we have given to us, which is 0, the 0.01. And in addition to knowing that x, we also know that the y is 1. So we can start this by figuring out what is the slope, what is the dy dx. Well, I'm going to highlight very prominently in yellow what our differential equation is, and we would always just plug in our known x and y in for that to figure out the slope, right? So 0 times 1, of course, is 0. And then we have all of the ingredients to write the equation of a tangent line, right? Point slope formula. So we could say y minus the y value equals the slope, quantity x minus the x value, which there's not much going on to that if you think. That 0 wipes everything out on the right side. And really, y equal 1 is about all you can do for your tangent line at that point. Okay. Now, last year, I know some of you, when we worked through this, were very confused about how to fill out some of the charts that we had associated with Euler's method. So I've kind of changed it a little bit here, and I've given a little bit more insight into what these last two columns are, because you guys really were very vocal about that, and I listened. So it says, let's figure out, well, what's this dy? Well, it says here that the dy in this case is just really basically what you get if you, and I think I've made a little typo here. I'm going to have to fix this. That is really the dy. Because if I take dy over dx and multiply it by dx, those cancel, right? So I apologize. I'm going to try to get that fixed for people that download this later. So the dy is simply what you have in this third column multiplied by the dx, which here is telling you is the same thing as the h. So if the h is 0.2, but my dy dx is 0, that means my dy is 0. That's basically telling you that the difference in the y values are the same at that point, right? Which might look like a good thing, but it's very likely that we're going to want to find a value on this equation somewhere besides when x is 0. In fact, I think later on it's going to end up being at 0.8, as we're going to find out. Okay. Now the y, capital Y column, is something that we're going to hold off on. We're not going to be able to complete that until we finish part C. And if you want to glance, well, what's part C all about? Well, part C is actually going to ask us to solve this differential equation, because we're going to be able to separate this and integrate that. I wanted to add that component to this because that's going to be a large factor of the next lesson over logistic growth. I just want to remind you about these differential equations as best I can. All right, so we'll hold off on the y prime, and now we'll go to the next row. Now the next row is solved by doing this. You apply your step, which is 0.2. So in other words, we're trying to figure out, okay, how far over are we going before we start writing our next tangent line? So the x value would be 0.2, 0 plus 0.2. And then the new y value is found by going back to the original tangent line and replacing any x that you see in it with 0.2. Well, that's a little hard to do here because there is no x value in that equation. So that means that the y is going to stay as 1. Now that might make you predict or think that the 1 is going to always be in this column, but you will be surprised here when we get to the third row that that will not be the case. So for the dy dx, we're back to the slope. It's pretty much lather, rinse, repeat at this stage. So x times y would be 0.2 times 1, or 0.2. And then the equation of our tangent line goes y minus the y value equal the slope, 0.2, quantity x minus the x value. Right? And it's certainly worth your while to clean this up a bit. So y would equal, you know what, if that's tough to do all at once, let's just do it this way. Y minus 1 equals, and then we'll distribute the 0.2. Nothing wrong with that. And we land here. And then if we get y completely by itself, I'll add 1 over. And so negative 0.4 plus 1 is positive 0.6. So hopefully everybody's comfortable with that at this point. Okay. And then remember, your dy is just really a matter of taking this dy dx, which is 0.2, and multiplying it by the h, which is going to give us a 0.4 here in this case. Okay, again, we'll hold off on the y prime. All right, we go to the next row. 0.4 is our new x. Hopefully that makes sense to everybody. The next y value I don't think is going to be 1 anymore. And we can find out what it is by going back to the original line prior, and we will replace the x with 0.4. So that would give us 0.2 times 0.4, which I believe is 0.08. And then you add 0.6, and the answer to that would be 0.68. That's going to be our new y value. And you can tell things might get a little rough here. Maybe we might have to break the calculator out. These problems are written in such a way that if you need the calculator, you're welcome to use it because of the nastiness of the decimals. But most of the time, if these are non-calculator problems, we stick with pretty integer values and we keep step sizes that aren't so ugly like 0.2. Now to find the dy dx, you would again take your differential equation x times y, and we would multiply those two values together, and you're going to see that I'm going to have to start implementing the calculator at this point. And I'm not going to drag it off to the side and show it to you, because I think that you guys can pretty much do these calculations on your own, or accept the fact that 0.4 times 0.68 is going to be 0.72 in this instance.
Mr.
Yes, sir.
You messed up your math. 0.2 times 0.2 is 0.04.
Oh my gosh. Way back over here. Thank you. 0.04. Yeah, is that the only line that's screwed up at this point? We good now? Thanks for that, you guys. Thanks. And yeah, feel free. Don't worry about. Yeah, just unmute yourself, because a lot of times I'm not looking at the chat and so forth. So, all right. So I think we're good up to the slope, right? So now we've got y minus our y value, 0.68, and that will equal our slope multiplied by x minus our 0.4. Okay. Remember, this is going to stay 0.4, right?
You still have. Would it still say? Why would it still say stay 0.4?
Right here, because on the left column, these x's, they really don't have anything to do with this dy dx column. What's going on? Yeah, what's going on with this x is that we're just adding 0.2 to each one of these previous x values.
Okay, so would it change in the equation of the tangent line though?
Well, I don't think the tangent line. Oh,
Yeah.
I see what you're saying. It wasn't just the calculation of, I'm with you, thanks. So I need to say 0.2x, thanks for that, guys, yes, plus or minus 0.04 here. So it does change there as well. So that will affect a few other things. This guy would be 1.04, if I'm not mistaken, right? And that will change this completely. So let's get rid of all this work. I was just rambling on with the wrong numbers.
Isn't it 0.96?
Yep, because we were adding 1 to negative 0.04. Thanks. Okay, and then the y of 0.4 would be 0.08 plus 0.96. And 0.08 plus 0.96 would be, what is that, 1.04? Is that right? I'm afraid to do any calculations anymore, guys. 1.04. Okay. All right. And this value here remains unchanged. 0.04 is still right. So the dy dx is now going to be taking 0.4 and multiplying that by 1.04, which is 0.416. So this is my new slope, 0.416. Okay, so we basically complete this process one more time here using the slope value we got. Sure didn't mess around with a problem that had pretty nasty values to it, did I? But I chose this for a reason, because it's one that we can solve and we can kind of look at some interesting characteristics. So there was a reason for it. So if I distribute the 0.416 into the x, and then I'm going to go ahead and do my multiplication here and say 0.416 multiplied by negative 0.4 produces something, and then I'm going to add my 1.04 to that result. The calculator gives me 0.8736. You probably don't trust me anymore, do you guys? 0.8736.
Nope.
That's what I figured. So that's going to be our new equation of our line. If we want to figure out what the dy is, again, we just multiply this 0.416 times 0.2. I'm at a point where I have completely sacrificed all my principles, and I'm totally fine using the calculator. So now the difference becomes 0.0832. And basically what you're finding out here is that the dy distance, which was pretty darn good at the beginning at 0, grew to 0.04, but now it's starting to whittle down a little bit. And I think that trend will continue. The next thing I have to figure out is when I go to my next line, and this is the last line that we have to fill out, guys, 0.6, is that I'm going to get a new y value out of this. So in the calculator, I'm going to take my 0.416 and multiply it by 0.6.
I think your y-intercept for the second one is wrong.
Oh my gosh. Okay.
I think it's 8736.
Yes, it is. It is. I've got it on my screen and I miscopied it. There we go. All right, so now 0.416 times 0.6, and then let's add the correct y-intercept, which is not there though, that's not good, right? Let's get you out of the way. There we go. Nope, out of the way. You out of the way, sir. Sir, you don't want to leave, do you? He wants to watch, guys. Now he's gone. And we'll get over to my other screen. 0.8736 now. And so I get 1.1232 as this new y value. That is 1.1232. And it sounds like there's a couple of you that are using the calculator to check me. Thank you. Thank you very much for that. dy dx is just basically these two guys multiplied together. So I will go ahead and do that with the graphing calculator off to the side. And that produces a result on my end of 0.6739. And then the last tangent line equation that we have to write takes y minus the y point, and we let that equal the very interesting slope now, multiplied by x minus 0.6. And if we get the y alone, we distribute the slope. And let's see what we've got here. If we were to take, whoops, get back here. If we were to take our slope and we multiply it by negative 0.6, and then we would add to that 1.1232. All right, and if you guys are checking along with me, that's perfectly acceptable and highly encouraged at this point. But I have a y-intercept of 0.7188. We could be off a decimal or so, but as long as we're correct to 3 places, we're good. And, you know, we kind of been blowing off this dy. I mean, I've been writing it. We kind of talk a little bit about what it means, but I'm hoping that we're starting to even get narrower and narrower here. So if we take this dy dx, which again was that point, that 0.6739 number, and if I multiply that by the step size, which is 0.2, we end up with something that's a little disappointing. 0.134. Well, that's not fun, right? 1,347. So it's kind of like dancing all over the place. It's like sometimes we're closer at certain instances, and then we move farther away. And I think it would continue to be pretty erratic. But we're going to abandon this here because now, well, we filled out the chart, right? That's what we're supposed to do. But when it says that, hey, let's use this to approximate y of 0.8, well, basically,
hey, Mr. Record.
Yes.
So sorry to interrupt.
That's okay.
How is there any particular reason that we're doing like 4, or is that something just that the table showed?
It's just something that the table shows, and I'm going to tell you, I don't really want you guys to have to do more than 4. Usually on the AP exam, it's 2. 2 iterations is fine. Sometimes in the homework, I might take you to 3, because the bottom line is if you guys can do this for 2 or 3 iterations, you can do it for 22. It's just that the math starts to get worse. But in the case of part A of this problem, I mean, the directions were pretty much complete the table. So we were sort of at the mercy there. But our ultimate goal really is what part B is all about. And unfortunately, we have to get each of these iterations taken care of first before we can jump to the point A. Does that make sense?
Yep. Thank you.
Yeah, no problem. So really this y of 0.8 is equivalent to, well, it's what we get when we take this 0.6739 multiplied by the 0.8 and add this 0.7188. And I'm going to go ahead and tell you what, this has got such a robust calculation to it. Well, the only thing is I can't cover up my work because I got to read it, but I'll let you, it's not going to do this, is it? There, how's that? So let's see if I got point. I'm just going to cheat and grab that, make it easy for me. Multiply by 0.8, and then if I add 0.7188, I get 1.258. We're going to go ahead and round that to 3 places now. 1.258 is what we're going to call this. And we just have to, accept the fact that that's our approximation. Right now, we don't really know if it's a good approximation or a bad approximation, but we can investigate that. And I think that's what part C is going to ask us to do. So, all right. So go ahead down to part C. And by all means, if you see an issue, guys, even if you have a question, you're not interrupting me. Just chime in if you've got a question, and I can certainly pause. I think that works best anyway. So this will bring back memories, right? Solve this differential equation with the initial condition. This is one of the easier ones. Remember when we would separate and integrate these? You want to get the y's on the left side, so we can divide by y. And we want to get the x's on the right side, so we'll multiply the dx over. So that is a separated differential equation. At this point, we can throw an integral symbol in front of both sides. And hopefully remember that the integral of 1 over y is natural log absolute value of y. And the integral of x is x squared over 2. And then if you recall, we only put our plus c on the right side. One could argue that there technically is a plus c on both sides, but because the c's are unbeknownst to us, we can just sort of consolidate them together, and we always want to do so on the right side because our ultimate goal is to figure out what y is. We want to solve this for y. Some of you like to solve for y right now by doing the exponentiation thing. Others of you like to plug in the 0, 1 to find c first. I have a mild preference. I think using that initial condition to find c is a little easier, but so many of you have lived your lives the other way and have been very successful with it. So I'm okay with that, but I do want to alert you to the fact that some cases, when you solve for C before, like I did, versus solving for after, you actually get two different C values, but yet once you solve for Y, your final answer matches the other way to go about doing this, okay? So in this case, C is just the natural log of 1, which is 0. It's like, wow, all that work to get nothing. So what we've got here is the natural log of the absolute value of Y equaling x squared over 2. And then at this point, we can go ahead and do our exponentiation step. And at that point, the E and the ln sort of kill each other. And temporarily, we have the absolute value of Y equal E to the x squared over 2. But then we can sort of look deeper into this and say, hey, the Y value in our initial condition was positive. And because of the fact that the solution to a differential equation must be a function, we don't want to run the risk of defining this absolute value with a plus or minus sign over here, because then we would lose the idea of being a function, because that's what the absolute value of Y is defined to be, right? The plus and the minus of an answer. So we can just do away with the absolute values and keep the positive version of this, because we knew we had a positive Y to begin with. And that's always going to work like that. It's very rare on the AP exam that they would put a negative value right there. And if they did, you would just have to put a negative in front of that E. The one time that they did it on a test years ago, it brought the scores down drastically on that differential equation problem. But, well, by 1 point. But it was a massive enough decrease that they thought, well, maybe that wasn't the best idea. But I want it to always be on your radar, you guys. So that would be the actual solution to this differential equation. And the reason I bring this up is, okay, well, let's just say what if we took E and let's raise it to the, what would be a good thing to raise it to? Let the X be 0.8, right? Let's go ahead and put a fraction in here. So 0.8, right, over, let's make sure I have the right thing, because I think I have to square something, don't I? So let's square all this. How's that? And let me double check. I want to say that that negative should not even be there, right? I don't know why there is a negative there to begin with. Why'd you guys put that negative there? Stop doing that. So that's what we're actually evaluating. And if we do so, we get an answer that's okay. It's in the ballpark. It's kind of a letdown after we've done series, you know, knowing how close we can come to a solution using Taylor series. But at least we know that we're within, well, if we subtract these two things, we're within 0.119, right? Which isn't so terribly awful. In fact, our chart said something to the effect of that we would be within 0.1347 at the 0.6. So it looks like we actually bettered that, right? If we were actually working on another row of this, that's what would show up there. Okay. Now, if you're wondering, okay, well, what really would fill in this chart if we wanted to go through the motions of that? I would say the easiest way to handle him is just to probably enter a generic E to the x squared over 2. And I can do that like this. And I think I can just simply say, okay, well, let's evaluate this such that, so I can put my control equal, which is my such that bar. Ooh, am I making sure? I need to make sure that let's make sure that my such that bar is after the whole thing. I think it's there now. Okay. So now let's try that such that again. And yeah, I think the such that bar is in the right spot. It looks kind of strange, but let's let X equal, and then I can put my braces, control right parenthesis, and I can evaluate this at these 4 numbers that you see here just to the left of the calculator screen. So that would be at 0, 0.2, comma, 0.4, and 0.6, and I'll get those values respectively, and I can go ahead and toss those into the chart here. This would be a 1. Oh, I want to toss them into the chart. My calculator went away. let's go ahead and slide it back here, and I'll just read them from my right screen. So this would be a 1, and this guy would be a 1.0202, and we're looking at 1.0832, and when we evaluate it at 0.6, we have 1.1972. So we just sort of see the progression of what our solution would be for these various x's as we move towards the one that we wanted to approximate. Okay, and I think there is a, if I'm not mistaken, another part of this question that says find the difference between the exact value of y1 and the approximate answer in part A. Well, if we have to do this, then what that would require is we'd have to continue writing another equation of a tangent line. Am I right? We haven't really figured that out. In fact, we would have like the beginnings of that next row, and we would have to figure out what the new y value is, which I think we've done a good job, right? 1.258, but we haven't done the slope, and we haven't done the tangent line, of course. And you guys, I'm not going to do that for you. I'm going to go ahead and pull the plug on this particular example, because I think the point's made about how we have sort of this erratic behavior between the difference of the y values at any given position on this particular solution curve. Honestly, the point of this video is just to get you acquainted with this Euler's method process, and you know, any little bit that I can do about reminding you how to solve a differential equation will pay some dividends later in the week, but I think that's going to come back to you very soon. Okay. This next and last example is so much shorter, you guys. And to be honest, it's a lot more poignant and a lot more timely, because you're looking at a differential equation here that you cannot solve and separate. Hopefully you guys look into this and see, yeah, man, there's nothing that you can do to this, right? I mean, if you add y over to the other side, yeah, it's going to move it to the left, but how are you going to get this dx over? You can't multiply it from the right side over now because there's a y plus in front. So you have something that's not separable here, which just simply means that Euler's method is so much more powerful. It's going to really do something that you couldn't do by any other means. Okay, so we'll run through this one just really quickly together. Then I might show you some cool calculator stuff, and we'll call it a day with Euler's method. So in this particular case, it says, consider this diff-EQ. The initial condition y of 0 equal 1, it says use Euler's method with 4 equal step sizes to approximate y of 2. 4 equal, but it doesn't tell us what the step sizes are, does it? Well, that's no fun. What the heck are the step sizes? Well, we have to figure those out on our own, right? Now, the chart's not drawn for you, but you can easily kind of fabricate one yourself if you want to use the headings x, y, there's your slope, dy over dx, and then of course you can put your line here. I do not care about the dy in this case or the capital Y. It's not requested in the information of the problem, so we won't mess with that. And if we start with our first x, which is 0, and our first y, which is 1, 0 minus 1 is negative 1. So it looks like we've got a line of y minus 1 equals the slope of negative 1 times x minus 0, which leads to what? Y equal negative x plus 1. So 4 equal step sizes, we got to get up to 2. If you move from 0 to 2 and you want to do so with 4 increments, that would mean our step would be 0.5, right? Or 1/2, right? You might find that when you're doing a problem without the calculator, it might be just as easy to use fractions. We'll see how that works here in a second. So for our new y value, we have negative this 0.5x that we just found plus the 1. So that's going to create a 0.5 for the y as well, which really makes for a very easy slope, 0. So this is going to be a pretty easy lines equation to write. Y minus 0.5 equals the slope 0, quantity x minus 0.5, and it looks like the whole right side gets wiped out, and y is equal to positive 0.5. Okay, the next x would be a 1, right? Step size of a half. The corresponding y is what we get if I take that 1, plug it in for the x here, where there is no x, so the y remains 0.5. Doesn't mean it's going to stay that way much longer. And then the slope would be x minus y, or 1 minus 0.5, which is 0.5. Right? Now, I'm going to go ahead and keep this in decimal form and see what you guys think. I don't know, it's probably not so bad. We're just about done anyway, that it may not make a big difference here if we rewrite it as a fraction. Keeping it as decimal, what would you get here? Y equal 0.5x, and then this would be a negative 0.5. If you add 0.5, wow, that's a y-intercept of 0. You don't have to write it, but I'll put it there for emphasis. So looks like that's going to be a pretty easy thing to work with. So the next value in our table would be 1.5 for x. The new y value is what we get when we take 0.5 times 1.5. Okay, this is where you could make the decision about fractions or decimals. I don't know, 15 times 5 isn't that terrible to do either. But if you think about this as a fraction 1/2 times the fraction 3/2, that just turns out to be 3/4. And that's what 1.5 times 0.5 is. It's 0.75. Okay, so we'll put it in decimal form just to kind of be consistent, but you could have always turned it into something otherwise. 1.5 minus 0.75 is a positive 0.75, and yes, the last time that we have to do this, y minus our y equals the slope, quantity x minus our old x, and the next step would take us to 2, but wait a minute, 2 is such a cool number, right? 2 is the value that we're really trying to figure out. So basically what would go into this little cloud is the actual answer to this problem, right? So if we just take our 2 and evaluate this, so I'm just going to add my 0.75 over right now, and I'm not going to, let's make that a plus, and you know what, it probably is just as easy if we just plug 2 in here, subtract the 0.5, 1.5 that is, get 0.5, and now we're looking at another fraction, 3/4 minus times 1/2, that might be a little bit easier. 3/4 times 1/2 is 3/8. Now I'm pretty much wanting to sort of divorce the whole decimal idea, and I think it's a lot easier, especially if I don't have a calculator, to do something like this, right? 6/8 plus 3/8 is 9/8, and it would be totally fine to call your answer 9/8. If you're really good with your decimal approximation, some of you are awesome with that, that's 1.125. Either one could be present in a multiple choice problem. Yeah, about that, a multiple choice problem with 4 iterations. I don't know, I'd be pretty mad if I was you if I saw that, but it's not likely. But again, by doing several iterations with 2 examples, it basically allows us to just not have to do nearly as many examples, period, right? And there is no part B for this. I know it has this kind of random A, but that's pretty much where this ends. Pretty chill, guys. There's not much more to it than that. On Schoology, I'm going to drag the Schoology screen in again, if you guys don't mind, and kind of go back to the main splash or landing screen here. This is again for period 2, but they all look the same. What I've got is an assignment. I'm trying to think, where did I put the assignment? Did I even post it yet? Yeah, here it is. It's at the very bottom. It's this homework. It's called Homework BC, Approximating Solutions Using Euler's Method. So any like practice work that I'm going to have you guys do this week, I'm just going to house them in the main landing page of Schoology. We really aren't in a unit. I know you saw that this was titled Topic 7.5, and you're probably like wondering, well, what does that mean? Well, that basically is the unit system, numbering system that the College Board has now adopted that you guys were not using this year, that the AB kids started. So, you know, they've done Unit 7, we're in Unit 8 right now, but this was a topic that I skipped. because it wasn't important for them. In fact, you were the last group to ever learn Euler's method in AB class. This was just a review. Later in topic 7, unit 7, I think 7.9, I think it is. That's what our topic is tomorrow, and that's logistic equations, which is going to be brand new for all of us. So what I wanted you to do in the Schoology homework is, you open this up. It's just basically a PDF file. And again, you could print it out. It's a lot easier if you're able to. I try to keep these fairly short. I know this one's 4 pages, and I don't want to eat up all your ink, you guys, but just use whatever discretion. If you want to do your work on a separate sheet, that's fine. But you've got just maybe 1 or 2 problems that have the lovely table. They'll actually have you do a little bit of graphing with it as well to kind of see some characteristics, see some relationships. And for the most part, it's a pretty short assignment as well. Just 5 problems, I guess. Figure that's about as much as you need. It's about as much you want to do, right? And it's going to be the case that we'll combine this topic with the logistic, and we'll create a little Schoology quiz at the end of the week that would be due Friday at midnight, and that's the last thing that you guys would be doing, really, for the most part, okay? So that's the case. Post photos of the finished notes. What I can do, Mackenzie, is I'll just take what I've got here in my Smart Notebook, and I can just save this or export this as a PDF file, and I can post this to Schoology. Probably, gosh, I'll probably. Maybe guys, if I start putting a lot of things on the landing screen, maybe it's best if I make some folders and call one of them completed notes and one of them homeworks. I'm sure whatever I decide, you guys are going to be able to find it. And if not, just ask me. So, yep, I can definitely do that. Hey, I almost made 45 minutes, didn't I? Almost there. Again, if we go back to the agenda screen here, one of the things that we didn't cover, just to try to get you out a little bit quicker, was the fact that your quiz key will be posted here in just a moment, and I will allow you guys to look at that through the week. But keep in mind, I am going to pull that down in a few days, and the reason is because if I don't pull that down and I export this, well, you know what's going to happen, right? Next year comes around and I open my Schoology and create my second semester, all of a sudden, this quiz key is going to be up there. So. All right, so that's the game plan. Charlie, I tell you what, I'm going to go ahead and I'm going to end the recording. I'm going to keep the stream going though, because if you guys have some other things to talk about, so I'm going to stop the recording. Thanks for joining us, everybody, watching the recording, and we'll see you guys in the next video.